everyone can hear me. Hello, everyone. So happy New Year. So welcome back. This is the first IRIM seminar for the new semester. So we are very glad to kick off this seminar series this semester with an excellent speaker, Professor Ani Majumdar. Ani is currently associate professor at Princeton in mechanical and aerospace engineering, and he's also affiliated with computer science, right? He also currently hold the part-time position at Google DeepMind. I guess you are doing sabbatical right now, exactly, right? And Ani received his PhD from MIT, and after that, he did maybe 1 year postdoc at Stanford before he moved to Princeton. Ani has a lot of excellent reward, including Sloan Fellowship, ONR Young USA Award, SF Career Award, and many, many more. So I think I don't need to mention all of them. He also gets a long list of best paper award, especially I personally know the IGR one a few years ago. This is the best paper award of the year, especially on I guess your early year work on this robust feedback motion planning ideas using the funnel ideas. I think these days his group change directions a lot, focus a lot on foundation models, and especially how to address some of this challenge from a more rigorous perspective. How to quantify uncertainties and provide formal guarantees and assurance. So I guess that will be the main topic he's going to talk about today. And so again, let's welcome our speaker today and look forward to a talk. Okay, Annie.
Awesome. Yeah, thanks so much, Ye, for the introduction and for the invitation to come visit Georgia Tech and present our work here. So as you mentioned, so our group works on, sorry, the clicker is not working. Just give me a second. Okay, there we go. Yeah, so our group works on enabling robots to operate with formal assurances on safety and performance in challenging environments. And these are some of the different systems that we've worked with over the years. More recently, so over the past maybe 2 or 3 years, we've been thinking about this dream that's animating a large portion of the robotics community, which is the dream of generalist robots. So robots that you can instruct on the fly via natural language, for instance, to perform a variety of different tasks in a variety of different environments. And right now, there's a lot of investment, a lot of money pouring into startups from industry entities, and also interest from academic groups. And there's a lot of optimism, I would say, right now, and especially optimism towards scaling. So scaling up data collection, so getting really, really large-scale teleoperation data from humans, scaling up other things like simulation to make progress towards this idea of generalist robots. And with this optimism, there's also a lot of work, a lot of effort that's being invested to these data sets, so large-scale teleoperation data sets like the OpenX embodiment data set or the Droid data set, and also lots of work towards models that are open source that you can kind of just download checkpoints for and just run them zero-shot without any fine-tuning in your lab. So this is the Octo vision language action model that's running zero-shot, so no fine-tuning whatsoever, just a little bit of tweaking in terms of lighting conditions and so on. It's running in our lab in Princeton. The goal here is the instruction is to place the carrot onto the plate. And you can see that it's kind of working well. What I want to focus on today, though, is some of the challenges that, at least in my mind, are still outstanding and that are going to keep us busy for the coming years. And in my mind, the main challenge has to do with reliability. So as an example here, again, with the Octo policy, what we did was we added a couple of distractor objects. So these are objects that are not relevant to the task of placing the carrot on the plate. So these are completely kind of just visual distractors. But these are sufficient for significantly degrading the performance of the policy. So this policy was working without distractors, add a couple of objects, and it no longer works. And we see this kind of challenge of reliability across scales. So across data scales, across model scales. This is OpenVLA, so it's a much larger model and trained on lots of data. That's again running zero-shot successfully under nominal conditions. But as soon as you add a couple of distractor objects into the scene, that breaks the performance of the policy. So I'll present some kind of quantitative numbers on this degradation later in the talk, but it's quite significant. Maybe one other thing that I'll mention is that these objects, these distractor objects, are actually from the data set that this model was trained on. So these are from the Bridge V2 data set. These are not some adversarial objects that we found to break the policy. These are kind of just random objects from the training data set that make the policy fail. So going kind of even further along the scale of data and kind of model capabilities to autonomous vehicles. So this is a video from maybe a year or so ago where someone was placing these objects in front of Tesla's full self-driving system in kind of very benign conditions, right? This is an open road, sunny weather, maybe as beautiful of a condition as you could expect. But this perception system, which was trained on gigantic amounts of data, like massive amounts of data, is failing to reliably perform in this setting. And maybe the most kind of extreme scale of data that we currently have available to us, so large language models, we see similar challenges with reliability. This is a paper from a group at Apple that came out a couple of months ago, where they were looking at these grade school math problems, GSM problems. So these are things like Oliver picks 44 kiwis on Friday, then he picks 58 on Saturday, and so on. But then there's this distractor phrase, but 5 of them were a bit smaller than average. So this phrase has nothing to do with the question or the answer. So it's sort of similar to the distractor objects that we were introducing for our robots. And these kinds of distractors are sufficient to mess up the performance of the LLM. And moreover, like the degradation is kind of across different models, so including the most recent O1 models, which are trained via reinforcement learning to do reasoning. There's a kind of almost 20% hit or more in terms of performance with these distractor phrases. So my takeaway from these observations is that reliability is a challenge across data scales. I don't think simply scaling up our kind of behavior cloning data is going to patch these vulnerabilities that we see with our current paradigm. So I think there are two logical ways in which you can address this. So one is somehow find maybe algorithmic innovations, theoretical techniques, or just scaling up to achieve extreme levels of reliability. And I'll say a little bit more about how we can do that later in this talk. The second approach, which might seem somewhat foolish, actually, if you think about it initially, is just deploy our systems without complete reliability. So let me talk about the second option first. Again, like I said, this might sound crazy to begin with, but it's actually something that we've done quite successfully for many years. Again, looking at autonomous vehicles as an example, until very, very recently, so until maybe about last year, we deployed autonomous vehicles on public roads without kind of fully complete reliability. And the way we did this was by having a human in the loop. So we had a human supervisor in the car, kind of ready to take over if things were going wrong. And that's the way we kind of patched the reliability issues that these systems had. And I would argue that we're actually doing something similar with LLMs now. So LLMs, like I argued, are not fully reliable, but they're real products that people pay real money for and find useful. And I think, again, the trick is kind of similar, which is that we have a human as part of the loop. So we're looking at the outputs of our LLM. We're deciding what to do. Maybe we reprompt the model with a slightly different question. Maybe we ignore the output, or maybe we rely on the output. As soon as you start taking the human out of the loop, bad things start to happen. There's a lot of excitement these days, especially this year, around LLM-based agents. So LLMs that can kind of take actions in your browser and so on. This is an example of a LLM agent that someone created with the Claude model. You don't have to read the text here. I'll just give you a quick description. So basically, this person asks the agent to SSH onto some computer in their network with some username. The agent did that successfully, so it's SSH'd into the computer. It then decided that the computer needed a bunch of software upgrades. So it decided to upgrade a bunch of the software. It then decided that the kind of sudo apt command was taking too long, and it upgraded the kernel of the machine, and the computer kind of stopped functioning at that point. So I think, to me, this is an example of the kinds of things that can go wrong when you take the human out of the loop, when you really have autonomous behavior without a human with these kind of unreliable systems. And I think the consequences that we might see if we deploy robotic systems that are not fully reliable could be, of course, much more severe since they're acting in the physical world. So what I want to focus on today is how can we deploy systems that are not fully reliable, maybe by bringing in a human back into the loop, or how can we increase the reliability of our current systems. So what I'm going to argue is that to be able to do these two things, to be able to increase reliability and also deploy systems that are not fully reliable, we need robotic systems that know when they don't know. So we need to have some strong and rigorous uncertainty quantification as part of our robots. And I'll present three projects that have this kind of theme of uncertainty quantification. So the first one is robots that ask for help. This was a paper that we presented at Coral in 2023, where the setting is one of language instructed planning. So you give a robot some instruction via natural language. It uses an LLM to come up with some plans. And it basically decides when is it confident about a certain plan, when is it not confident. And if it's not confident, it asks a human for help or clarification. The second project is work we presented at RSS last year, where instead of querying the human for help, what the robot does is it queries the environment. So it does some active exploration, information gathering to help it reduce its uncertainty. And our most recent line of work, so bring your own VLA, the goal here was to use uncertainty quantification to improve the reliability of our current vision language action models, VLA models. Okay, so the first work, so robots that ask for help. This was a collaboration with people at Google DeepMind, or at least people who were at Google DeepMind at the time. And yeah, like I said, we presented this at Coral 2023. The setup here, just to kind of ground things, is you provide a robot a language instruction. So like place the bowl in the microwave, please. In this case, there's some ambiguity. So there are two bowls. There's a metal bowl and a plastic bowl. And at the time that we did this work, 2023, the state-of-the-art model was GPT 3.5. And if you gave it this prompt, let's say you asked it, I have a metal bowl, plastic bowl, which one should I place in the microwave? It tells you to place the metal bowl in the microwave because it's more likely to be able to withstand the heat from the microwave without melting or getting damaged. Of course, this is exactly the wrong thing to do. So you should not be putting metal objects into your microwave because they can lead to a fire. So what we would hope from our robots in this kind of ambiguous or potentially ambiguous setting is that they should know when they don't know and should ask for help instead of just blindly following whatever plan your LLM came up with. So in this case, the robot should ask, which bowl did you mean, the metal bowl or the plastic bowl? Which one should I pick up? So currently, so our LLM-based systems and also other systems often don't know when they don't know. This is a kind of famous example of how many R's are in strawberry. This was a question that tripped up language models until recently. So yeah, they would say there are 2 R's in strawberry. You can ask it, can you check again, please? It says, OK, I checked again. It's still 2 R's. You ask it, are you 100% sure? It says, yes, I'm 100% sure. Would you bet $1 million on this? Yes, I would bet $1 million on this. So this is self-verbalized confidence. So the model is telling you in the tokens that it's outputting that it's 100% confident. Of course, this is wrong. You can also kind of look under the hood. You can look at the underlying token probabilities, the log probabilities that the model is outputting. And again, we see similar issues there. The prompt here is there are 3 drawers. Which drawer has the Coke? So very ambiguous situation. But somehow the model is 93% confident that the Coke is in the bottom drawer, even though there's no kind of a priori reason that this should be the case. Things get even more kind of subtle and challenging when you look at quantifying uncertainty over entire sentences. So the most common way of doing this is something called perplexity, which is basically looking at the log probabilities, aggregated log probabilities across all the tokens, across all the characters in your sentence. So maybe just to illustrate this, the prompt here is there's a Sprite and a can of Coke on the counter, and the instruction is to put a drink in the middle drawer. And let's say you're considering two different plans for your robot to possibly execute. So the first plan is I will put the Coke in the middle drawer. The second one is I will put the can of Coke in the middle drawer. So these are actually semantically identical because we've already specified that it's a can of Coke. So the only difference between these two plans is the length of the sentence, like just the length of the description. And as you can see, if you look at the log probability for this versus the log probability for this, the second one has a significantly lower probability. And intuitively, this should make sense. What's happening here is that we're multiplying a bunch of probabilities together. And if you multiply more of them, you're going to get a smaller number. So this is a bias that you introduce when you have longer sentences. So in this work, what we were trying to do was address some of these challenges. So we wanted a way to do rigorous uncertainty quantification for our LLM-based planners with the goal of having some calibrated confidence. So we want the robot to ask for enough help from humans to get to some statistically guaranteed level of task success. At the same time, we don't want the robot to be constantly pestering the human. So we want the robot to act independently as much as possible. So we want to minimize the amount of help that the robot seeks. So I'll describe the kind of main elements of the approach that we took here. So we call it no, short for know when you don't know. And the two kind of main technical ingredients are first, to pose the problem of language instructed planning as a MCQA problem, so multiple choice question answering problem. This is going to help address the length bias issue that I mentioned previously. And the second kind of main component here is to use conformal prediction for rigorous uncertainty quantification. So I'll provide just a kind of overview of the general architecture before describing some of these technical aspects. So initially, you give the robot some instruction, place the bowl in the microwave, please. You provided some additional context, maybe of things that are relevant in the environment. And then you prompt your language model to come up with some diverse set of plans that could be executed given the instruction and given the environment. So in this case, the plans that it comes up with are put the plastic bowl in the microwave, put the metal bowl in the microwave, and so on. So 4 options here. And then we manually append some option E, which is none of the above. We then reprompt the model. So you can think of this as a multiple choice question answering problem. So you're given some question, you have some possible answers, and you want to select one of these multiple choices. So we reprompt the model and ask it, OK, which of these choices would you select? And then we look at the token level probabilities on the tokens A, B, C, D, E. And that's our kind of heuristic confidence that's coming from the large language model. And this is where conformal prediction comes in. So these confidences are not really kind of calibrated in any frequentist sense. So what conformal prediction does is it specifies some threshold on confidence above which you consider plans. So any plans that have a confidence that's above the threshold, you're going to kind of place into this, what I'll call a prediction set. So in this case, there are 2 plans that are above the threshold. So put the plastic bowl, put the metal bowl in the microwave. If this set has size 1, then we consider the kind of robot to be confident, and it executes that plan that was selected. If this set has size larger than 1, then that triggers a call for help from the human. So the LLM generates a question that tries to disambiguate between these two different options. So in this case, it says, which one, plastic or metal? The human provides some clarification, the plastic one. And then we assume that there's some low-level policy that's responsible for actually physically executing the plan that was selected. And this whole kind of cycle repeats. So you do this in a receding horizon fashion. So you generate plans, you execute a portion of it, you decide whether to query the human or not, and you keep going until the episode ends. I think I saw a question. Yes, yeah. So I haven't explained it yet. So for now, just think of it as some black box method that specifies this threshold. I'll describe exactly how that works in a bit. Yeah, this is the rough architecture question. Yeah, so okay, at the time that we did this was pre-GPT-4V. We were just using an LLM combined with like an open vocabulary object detector. Yeah, nowadays there's no reason to do that. Just use a VLM. Yep, good, cool. Okay, so yeah, so I mentioned that there are these kind of two aspects. So multiple choice question answering. So what's happening here is that we give it the instruction, we prompt the model, generate some options, and then we reprompt the model to get the confidences on just the single tokens A, B, C, D, E when we ask it which of these options is correct. What this does is it eliminates the length bias. So we're no longer looking at probabilities across multiple tokens. We're just looking at the probabilities of single tokens A, B, C, D, and E. And yeah, this kind of gets rid of the length bias issue that I mentioned previously. This also aligns very nicely with the training objectives for LLMs, which kind of naturally have to do with next token prediction. So that's the first part. So getting rid of this length bias. The main part is this conformal prediction-based uncertainty quantification, which kind of specifies this threshold that I mentioned previously. What conformal prediction allows us to do is provide some pretty nice statistical assurances on task completions, on the correctness of uncertainty quantification. The main, maybe kind of technical feature of conformal prediction that's appealing is that it doesn't make any assumptions on the nature of the distribution of inputs that your system receives. So in our case, it's the distribution of instructions or environments that you place your robot in. We don't assume kind of explicit representations or explicit knowledge of that distribution. What we do assume is some representative samples, so some IID samples from that kind of potentially complicated unknown distribution. It's very computationally lightweight and easy to use, and over the past year or so, we're kind of seeing increasing use of conformal prediction in robotic settings. Maybe just a quick show of hands. I guess how many people are already familiar with conformal prediction? Okay, actually, yeah, decent number. All right, good. So I'll provide a brief overview of what conformal prediction does. I won't go into the details of how it does it. I'll just say what it does. So the inputs to conformal prediction are two things. So the first one is some pre-trained model. So it takes some input X, and it produces some heuristic confidences. So if you're doing image classification, think of these as probabilities kind of roughly on your different classes. If you have a language model, then these are the token level probabilities. More importantly, what conformal prediction assumes is this calibration data set. So you assume that you have some labeled examples from the distribution of inputs that you care about. We don't know what that distribution is, so it could be very complicated, but we assume some IID samples from that distribution. So with these two inputs, what conformal prediction does is it produces what you can think of as a new model. Really, it's a wrapper around your old model that for every input, so for every input X, it produces a prediction set. So a set of labels, a set of possible answers that it generates. Maybe just to make this concrete, let's say you're doing kind of ImageNet style, like image classification. So the input here is the image, that's X. Typically, the label would just be like cat or dog or squirrel or whatever, just one label. But here we're going to produce a set of labels. So this is our prediction set. And the size of that set you can think of as a kind of rough indication of how uncertain my model is. The main statistical guarantee that comes from conformal prediction is a guarantee on coverage. So you can specify some confidence threshold, 1 minus epsilon, and with that probability, these prediction sets that are generated for new examples beyond the calibration data set, but from the same distribution, the prediction sets will contain the ground truth label with that user kind of specified probability that you specified. So that's the main guarantee that conformal prediction gives you. So these prediction sets will contain the correct answer with probability 1 minus epsilon. So in our setting, the way this works is we come up with some plans given some instruction. We prompt the model, get these token level probabilities. So these are just raw heuristic, uncalibrated probabilities that come from the language model itself. And conformal prediction specifies this threshold. So this is the way the prediction set is constructed. So the prediction set is constructed by including all options that are above that threshold. In this case, there's only one option. So there's option B, put the apple in the compost bin. In that case, the robot is confident, it executes that plan. If this prediction set has size larger than 1, then that triggers a call for help. And it asks the human, what should I do? Help me select one of these plans. And the human provides some clarification. OK, so I mentioned, yes, question. Yes, of course. Yes.
So you said that you want the correct answer
to
be into the return set.
Yes. Yep. Yeah.
But in the example that you had there somewhere,
yeah,
you have some weights, some probabilities. I don't know what exactly it is.
Sure.
Yeah. The numbers.
Yep.
And are there supposed to be some loss expression of confidence?
Yes. Yeah.
So what if, yes, we have the correct answer in the set,
yeah,
with a very low confidence level.
Yeah. Good. Yeah.
To the requirement that you have there for
yes. Okay, good. So
correctness or not?
Yeah, so maybe I'll explain it actually with this slide. So what conformal prediction always guarantees is that it's going to find some threshold such that this coverage guarantee is valid. So it could be that for some epsilon fraction, you're wrong. But with probability 1 minus epsilon, the true label will be in the prediction set that you generate. By itself, this guarantee is actually completely trivial because I can always do this. I can always say I'm always uncertain. No matter what question you ask me, I'm going to just say I don't know. I'm going to just output all my labels. So what conformal prediction also does kind of additionally is it approximately minimizes the average size of the prediction set. And how small or large your prediction sets are depend on how good those underlying probabilities that come from your model are. So if those probabilities are already good, like are already kind of well calibrated, then these prediction sets will actually be optimal. They'll be like very small. If, like you said, the model is has the correct answer but with a very low probability, and it's, let's say, confidently wrong very often, then these prediction sets will be large. So conformal prediction basically figures out how large or small to make these prediction sets in order to have this guarantee. So this is always satisfied. This is a kind of soft objective. Yeah. OK. So these two properties of conformal prediction kind of map directly onto the things I mentioned. So because of this coverage guarantee, because the prediction set is guaranteed to contain the correct plan in our case with probability 1 minus epsilon, that translates into a guarantee on correctness of what the robot does, so task success. And because conformal prediction is minimizing the average size of the prediction set, that addresses our goal of minimizing the amount of help that we're asking from humans. So we have a couple of extensions that we have in the paper. So one extension is settings where there might be multiple possible kind of valid answers. So maybe there are multiple plans that are all equally satisfying. In this case, what you want is your prediction set to contain at least one acceptable plan. This is a relatively simple technical extension. The much more kind of technically involved extension is when you're doing planning in a receding horizon fashion. So you make some sequence, or you plan a sequence of steps, you execute a part of that, you replan, and maybe you ask a human for help, and you kind of do this in a closed loop receding horizon fashion. The challenge here is distribution shift. So because your actions now influence future observations, the distribution of future observations depend on the actions that I take at this time step. And yeah, that causes some issues. The main kind of idea here is to lift all your data to episode level sequences. So instead of looking at data time step to time step, you look at data in chunks, so in episode kind of level sequences, and that addresses a lot of the issues with kind of non-IID data that you have if you look at time step to time step observation. So I won't go into the details of this. I'm happy to answer questions later, or obviously feel free to look at the paper as well for this extension. Okay, so I'll present some experiments here. So we evaluated this both in SIM and a couple of different hardware platforms at Google DeepMind.
Could you put the bowl on a small counter in a microwave?
I guess this was the running example I was using previously. So it goes up to the bowls, yeah, generates these plans. This is the prediction set.
Pick up the plastic bowl, please.
I guess one thing I'll mention here is that we made this very strong assumption that once the language plan is selected, you have some low-level policy that executes it, and that's a big assumption. So here, I think we were using RT1 or RT2. That's the VLA model from Google to actually go from that plan that was selected to actual kind of motor commands. Here, there are two modes of ambiguity. So put the soda in the drawer, which soda, which drawer. So it actually clarifies both. This one is interesting. This is an example of what's known as a Winograd schema that linguistics folks used to worry a lot about. So there's the kettle chips in Red Bull. I ate it already. Can you dispose of it? So there's some ambiguity in the word it. So you need to use some common sense reasoning to say that I can eat kettle chips. I cannot eat Red Bull. So when the person is saying it must mean kettle chips rather than Red Bull. This is actually something that LLMs today are extremely good at, and we don't worry about these Winograd schema type questions anymore. And so yeah, there's no help that's needed. The robot is confident. It just executes that plan. We tried this on other problems as well. So this is a tabletop rearrangement problem where the robot is presented with some partial preferences that a human has on kind of food items, and it needs to sort other items of food based on whether or not it thinks the human is going to like them. And if it's not confident, then it queries the human and asks, do you like this food or not? So yeah, that's kind of the setup here. So we also did some quantitative kind of comparisons with a whole bunch of different baseline methods. Maybe the simplest baseline is where you just directly use the uncalibrated scores. So you get rid of conformal prediction. You just look at the uncalibrated kind of confidences that come from your LLM. There are also other techniques like kind of Bayesian style techniques like ensembling that people have used for uncertainty quantification for many years. There are just kind of direct prompting. So you just ask the model to generate some prediction set. You ask the model, like, are you confident or not? So this kind of self-verbalized confidence. No help, where you just, the robot always executes the plan that had the highest confidence. And what we found was that, so these are different kinds of ambiguity that we evaluated. And across all of these, conformal prediction helps you decrease the amount of help that's required as compared to the baseline. So here we're fixing the task success rate. And if you kind of pin the task success rate, the amount of help that's needed is significantly less when you use conformal prediction as compared to these baseline techniques. We also have some extensions of this. This was work we presented at RSS last year, where instead of just calibrating this one scalar quantity, which is the confidence threshold, you can also tweak other things. Like if you have some temperature parameter in your model that changes the way the probabilities are generated, you can kind of calibrate that as well, and that also helps improve performance. Okay, so the first project, the thing that uncertainty quantification allowed us to do was ask a human for help. But I think what I want to show next is that's not the only thing that we can do with uncertainty quantification. So in this next work, what we thought about was how can we use uncertainty quantification to decide when to explore the environment. So maybe there's some uncertainty. Maybe I can kind of go out and explore the environment to resolve that uncertainty. How do we do that? This was a collaboration with Dorsa Sadiq's group at Stanford and also Masha Itkina from TRI. And again, the paper was presented at RSS last year. The setup here is one of embodied question answering. So you ask your robot some question like which item is on the armchair next to the bedroom dresser. You give it some multiple choices. And the robot needs to explore relevant regions of the environment, and it needs to stop when it thinks it's kind of confidently able to answer the question. And the role that uncertainty quantification plays here is to basically figure out when should it stop or when should it ask the question. Sorry, this went by kind of quickly. So maybe let me just play this again. So this is an example of what it looks like. So is my kid on the treadmill, yes or no? So the robot explores different parts of the house, gets to this image, and then says, no, my kid is, or your kid is not on the treadmill. So there are kind of two parts to this approach. So the first one is figuring out where should the robot explore. So for this, we were using VLMs, so vision language models, to basically guide exploration. So you can ask VLMs kind of open-ended questions, like is my TV turned on? You can also ask it things like where is the sofa likely to be? And it gives you some response, like the sofa is likely positioned against the wall to the left because I can see a coffee table, and this is a kind of common setup for a living room. So the idea here was to use this kind of semantic reasoning capabilities of VLMs to guide where the robot should explore. One challenge is that the VLM's kind of semantic reasoning is not grounded in geometry, so it's not grounded in some geometric map of the environment. So in this work, we combined the semantic kind of reasoning capabilities of VLMs with some kind of explicit geometric map. So we're storing, so this is sort of like frontier-based exploration where we store what we've already explored, what we've not explored. And we use the VLM to decide where to explore next. So again, an example, so consider the question, is the outdoor grill covered? We ask the VLM, which direction would you explore? So we have this way of generating different kind of plausible candidates for exploration, and we label those in the image. And then we give that kind of labeled image to the VLM, and we ask it, where should we explore? And again, we're looking at the token probabilities for these different options. And I'm going to call this the local semantic value. So these confidences on what are the promising directions for the robot to explore. The challenge here is that there might be cases where, let's say your robot is just facing a blank wall. If you ask it, should I explore A, B, or C, it'll say just 1/3, 1/3, 1/3. But all of those are kind of equally bad directions to explore because there's no information that your robot has. So we also ask the VLM, is there any direction shown in the image that's worth exploring? And we look at the probability of the token yes, and we call this the global semantic value. And what we do is we just combine these two different things. So we multiply the local semantic value with the global semantic value. And we store that combined semantic value in a geometric map. And that's what we use for exploration. So we're using, so we use frontier-based exploration. So we get the robot to go to some region kind of on the frontier between explored and unexplored regions. And we're using the semantic value to decide what point on the frontier to explore next. So there's a lot of classical kind of work on frontier-based exploration, so kind of going back decades. More recently, people have thought about how to use learning-based techniques to guide exploration. And most recently, people have been thinking about how to use foundation models for exploration. At the time that we did this work, most of the prior work basically assumed that there was some pre-built representation that you give to your kind of foundation model. The most recent work, or most relevant work rather, was actually from folks here at Georgia Tech. where they were also using VLM to guide exploration, but we're using a kind of clip style cosine similarity between text and image instead of using the VLM's token probabilities. And what we found was that using the token probabilities from the VLM rather than the kind of clip-based scores led to more efficient exploration. And we also found that combining this kind of local semantic value with the global semantic value helped improve the efficiency of exploration. So that's one component of it. So how do we use VLM to guide exploration? The other piece is the uncertainty quantification piece. So how do we know that we're done, right? How do we know we can stop and answer the question confidently? Again, we're going to kind of leverage the VLM's confidence. So we ask the VLM, so given the current view, are you confident about answering the question, yes or no? So we look at the probability of yes from the model. Again, the main challenge has to do with miscalibration. So these confidences that are coming from the VLM are not calibrated in a frequentist sense. So the model can be confidently wrong pretty often. So as an example, so if you ask it, is the TV turned on? It should be pretty confident here, but actually it's just 0.2. If you ask it, is the outdoor grill covered? This should be a bit harder, but actually somehow it's more confident here. But both of these are pretty low confidence. And we see this across the board. Yeah, these confidences are either kind of very high or very low. I can explain maybe in the discussion why this is. So it has to do with the RLHF process, reinforcement learning from human feedback. That actually really messes up the calibration. But either way, these confidences are not particularly well calibrated. And the approach that we took is very similar again. So we use conformal prediction. So we generate these prediction sets and we intersect them over time. And at the end, if you're left with just a single answer, then you're confident and the robot stops and answers the question. And the guarantee that comes from conformal prediction, again, is same as before. So with probability 1 minus epsilon, the intersected prediction sets are going to contain the ground truth kind of correct answer with that user-specified probability. So as part of this work, we generated this new EQA embodied question answering data set that has questions of many different types. So identifying things, counting things, answering questions about the existence or state of things or the location of things. So I think we have about 300 or 400 different questions as part of this new data set. And we evaluated this in the habitat simulator, so in simulation first. Maybe just some representative examples. So is the lamp next to the sofa turned on? This is showing the portions of the environment that were explored by our method, by a frontier-based exploration method, and this clip score method. And as you can see, with our method, the exploration is a bit more concentrated because it's using the kind of semantic reasoning from the VLM to guide where to explore. Another example, this is the one I showed before, is my kid on the treadmill. This is showing the points that were explored, and you can see it's pretty concentrated exploration here. We also tried this on a real robot. So this was at Stanford. The question here is, what kind of stools are under the whiteboard? Initially, the robot gets a small glimpse of the whiteboard. So it reduces its uncertainty to A and D. And then it keeps exploring, and then eventually it kind of sees, this is the first person view. So it sees the stools, and it says lime green wants option D. Another example here, so is my dishwasher open or closed? So it gets to this view and is confident and says it's open. Okay, so maybe just in the last portion of the talk, last few minutes, I want to highlight some recent work that we've done on using uncertainty quantification to improve the reliability of our models. So in the first 2 lines of work, we were using uncertainty quantification to either ask a human for help or to explore the environment. Here we're going to try to do something a little bit different. So I'm going to go back to the videos that I opened the talk with. So this was these vision language action models that are kind of working well under nominal conditions, but as soon as you add some visual distractors, they fail pretty dramatically. And just to quantify the degradation in performance, so without distractions, with Octo, the performance is roughly 70-ish%, slightly under that. If you add these visual distractors, again, these are distractors from the data set, from the training data set, the performance drops from 67-ish% to 27%. This is across maybe 20-ish trials. Background distractors, we see a similar thing. So background distractor here is when you change the color of the kitchen kind of background. Again, nothing adversarial. The performance drops by a similar amount. And we see similar things with OpenVLA, which is a much larger model. If you change the objects, add some distractor objects, change the background, the performance takes a very significant hit. So what we were trying to do here, or the question we kind of asked ourselves is, can we take these pre-trained models and not do any fine-tuning on top of them? So just take the pre-trained models and do some intervention at runtime. So as your robot is operating, as you're executing the policy, can you somehow change the observations that are being fed into the model to make the model more visually robust? So let's say this is the original image, and your VLA is brittle to these distractor objects. We want to change the observation in a way that's going to make it not brittle to the distractors. And the idea we had was pretty simple. So can we use these modern image editing tools, so things like in-painting, out-painting, to basically get rid of objects that the model is paying attention to, but that are actually not relevant to the task that the model is trying to perform. So I'll give you a quick sketch of how the approach works. The first step, again, is to use a vision language model. So we give the instruction that we've given to the robot. So place the corn in the pan. So we give that to the VLM. And we ask it, given that your robot is trying to achieve this task, what in the environment is not relevant to this task? And the VLM says the sink is not relevant, the bottle, the olive oil, the yellow wall, these are irrelevant things. We then use a grounded segmentation model, so grounded SAM, to segment out these irrelevant portions. And this kind of second step is the main uncertainty quantification step. What we are trying to do is figure out what is the model paying attention to, like what is it sensitive to that's not relevant to the task. And the way we do this is we take our original RGB observation and we perturb these different segments, irrelevant segments. So in this case, we're adding some Gaussian noise to this background element. And we compare the two actions. So what happens with the original observation, what happens with the perturbed observation, how different are they? And this difference in action basically quantifies how sensitive your policy is to this kind of visual element in the scene. And we do this for all the different irrelevant things. Here we're Gaussian blurring this olive oil bottle. Here we're adding some Gaussian noise to the sink. So we do this for everything that the VLM said was not relevant. And at the end, we end up with this heat map of sensitivity. So this is what the model, or this is quantifying what the model is kind of paying attention to when it shouldn't be paying attention to them. And then we have some threshold that we pick. Anything above that threshold, we use image editing, so just automated image editing at runtime to basically eliminate or modify that visual region. So if it's some object that the model is paying attention to, then we simply outpaint that object. If it's some kind of larger, maybe background element, then we just change the color of that element until the model is no longer sensitive to it. So that's roughly the approach. Maybe let me show you what this looks like when you run your policy. So here the instruction is put the eggplant in the pan. This is with OpenVLA. These are the observations after the automated edits. So as you can see, the observations are being edited to eliminate things that the model happens to be kind of spuriously paying attention to at that time step. Here's another example. This is with Octo. And these are on the right are the observations at runtime, the edited observations that are being fed to the vision language action model. One thing that I'll mention here is one limitation of this work is the amount of time it takes. So initially, we query the VLM to figure out what is relevant, what's not relevant. That takes a couple of seconds, but we just do that once at the beginning of the episode. And this image editing and kind of sensitivity analysis, we do that at every time step. And that takes on the order of 1 to 2 seconds. So this is kind of real time if you're operating very slowly, but it definitely adds some amount of lag to the policy. But I think these image editing models are getting better quite quickly. So I imagine that we'll have pretty fast, closer to real time image editing in the next couple of years. So some quantitative kind of numbers on the improvements that we get with these runtime observations. So using these runtime observations, we're able to boost the performance back up to the nominal level of performance for Octo with object distractors. Also similar kind of performance with background distractors. And with OpenVLA, again, we see a pretty significant boost in terms of performance with these object and background distractors. Okay, so let me end with just some kind of concluding thoughts. I presented these 3 lines of work where we were using uncertainty quantification to clarify things, ask humans for help, to explore the environment, and to do these runtime interventions to help improve reliability. I think there's still a lot of work left to do. These are some initial steps, at least in my mind, that we've taken. One question that I find interesting is figuring out where exactly is the uncertainty. Is the uncertainty coming from some very ambiguous instruction that the human gave me? Is the uncertainty coming from some partial knowledge that I have? Maybe the human's instruction was perfectly fine. It's just that I have some partial observation and I need to go explore the environment. Yeah, what should I do? Where is the uncertainty coming from? Yeah, just kind of more broadly figuring out what component of the autonomy stack is causing the uncertainty and how can I remedy that? That I think is a promising question to think about. I think uncertainty quantification also has an important role to play in data collection. So it can help guide data collection. So if you know what you don't know, you can go out and collect more data to help patch some of the issues that your policy might have, some of the vulnerabilities that your policy might have. And finally, I think uncertainty quantification also has an important role to play across the autonomy stack. So in this talk, I was mostly focusing on kind of high-level decision-making with foundation models. But you can also do similar things with perception systems. So let's say you take some pre-trained bounding box predictor. These things are pretty good and are getting better, but they're not perfect. And they can break when your deployment environments are different from the training environments that these systems were trained on. So one line of work that we have is how do we take these kind of unreliable outputs from a pre-trained perception model and how do we calibrate them? How do we modify their outputs? Let's say we inflate the size of the bounding boxes that we get to be able to provide some statistical assurances on the correctness of your calibrated outputs. So we had some work that we presented at Coral last year where we were doing this. So we took some bounding box predictor. We used conformal prediction to modify the size of the bounding boxes such that we have the statistical guarantee that the inflated bounding boxes contain the true object with some high probability. And we also had a way of providing end-to-end guarantees. So when you take your perception system, you close the loop with your planner. This creates some kind of interesting challenges having to do with distribution shift. And we had some methods to address that as well. I won't go into the details, but I'll just kind of point you to the paper from Coral. So that's basically what I had today. So this is our group. So currently 8 PhD students, 2 postdocs. Alan Wren, who's about to finish up and graduate, he was the one who led our work on robots that ask for help, and also our exploration work, along with Anushree Dixit, who is a postdoc in our group and is now faculty at UCLA. And Asher Hancock led the work that I presented at the end on runtime observations, runtime interventions. And yeah, we're always interested in kind of adding to our groups. If you're interested in PhD positions, postdoc positions, definitely feel free to reach out. And I'll kind of just end with this final thought. So I see what I presented today as some initial steps towards doing rigorous uncertainty quantification for our foundation models. There's lots more to be done, and hopefully I've gotten at least some of you interested in doing that. So I'll end here and take any further questions you have. Thanks. Yep, go ahead. Yeah. Yes. Yeah. Yep. Yeah. Yeah, hugely important. I think a lot of thought needs to go into making sure that the calibration data set you have is representative of your deployment environments. So I think, spending a lot of time curating that calibration data set, like making sure that it covers the main modes of variation or uncertainty that you might see at deployment time, I think is super important. Another piece that I'll add that I didn't mention today, but runtime monitoring as well, I think can play a big role. So I would say do the best you can in getting a good calibration data set. But at runtime, we should also be doing some kind of anomaly detection or auto distribution detection. And yeah, if you find that your deployment environments are not from the same distribution or have kind of deviated significantly from your calibration distribution, then you should stop and maybe kind of retrain your policy or recalibrate your system. So I think both of those pieces are important, getting a good calibration data set, but also doing runtime monitoring. Yep. Good. Question? Sorry. Yeah.
Is fuzzy logic still in this business, uncertainty modeling?
Yeah. Not that I have seen. So I know it was kind of really popular in the 90s, but it seems to have become less popular. Yeah, not that I've seen anyways. Yeah. There's another question here.
Yes. So in the robots that ask for help, given that the user is, I'm guessing he's the expert on this one, and it's giving an update to the information.
Yeah.
Does the robot update its own information so the next time the situation does happen,
Yep.
the robot doesn't have to ask it?
Yeah, that's a fantastic question. It's not something we did here, but yeah, it's definitely something we should be doing. So we should be updating, let's say, the preferences or the estimated preferences that the robot has on what the human wants, or just kind of with the microwave example, right? Maybe it should update its knowledge of the world to be like, okay, I shouldn't be putting metal balls in a microwave. We were not doing this here. It's something that we should do. Another aspect of that is actively kind of asking the human like more questions to figure out what it should or should not do. Some kind of active preference learning. That's something we didn't do again, but I think is also important and a good research question.
Just a follow-up on this one. What about like bad? How does the system handle that? Like clearly, it's like, oh yeah, you want the metal ball.
Yeah.
The human says something.
Yeah. So it's not something we handle here. So here we are assuming that the human is kind of providing correct answers. But I think that's also a good question. Good. Yeah. Other questions? Yeah, go ahead. Yeah, that's a good question. So I mentioned that the reinforcement learning from human feedback, that part actually is what messes up the calibration. So in the robots that ask for help, project, because we were collaborating with people at Google DeepMind, we had access to their PaLM2 model, which was instruction fine-tuned, but not gone through the RLHF process. So the kind of general theme that we noticed was, yeah, if you have a model that has been instruction fine-tuned but not gone through the RLHF process, you should use that as your kind of confidence, because those are much better calibrated. And as soon as you pass it through RLHF, that really breaks the calibration. Yeah. Question.
With the models like Cosmos, which are like video world models,
yeah.
some of the there you can improving the uncertainty concentration perhaps in the conformal set.
Yeah, the video models, I'm not absolutely.
Even action conditional now.
Yeah. So I guess with the diffusion model is like maybe you can get some again heuristic notion of uncertainty that comes from the diffusion model itself. So I could see things being useful there. Yeah, I don't have a good answer to that. I think, yeah, maybe I have too long of an answer, which is I see some limitations with the behavior cloning paradigm that we currently have. And yeah, maybe some kind of like world model, like whether it's a video model or some world model in a latent representation space can help us both improve performance, but also help us do better uncertainty quantification. Yeah, I don't have super concrete ideas, but that's got sort of my gut instinct.
Rolling out in the video world model and
yeah.
using that data as a one set, like the set that you have.
Yeah, that's possible, but then you have to rely on the correctness of the video model, which is a big assumption too. So yeah. Yeah.
Okay, all right. For the sake of time, let's thank our speaker again. And if you have questions, you can talk to Ani.
Thanks very much.